Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Module 5, Refraction and Reflection Seismology. In the lecture 4 today, we are going to cover following concepts. First, we will have a recap of what we have learnt in the previous lecture. Then, we will see Earth as a constant velocity distribution. And then, we will make a formulation for intercept slowness for travel times. Then, we will have a summarized view of what we have learned today. So as far as the recap of previous lecture concerned, we learned that the study that uses the reflected arrivals to determine velocities within the crust and other geophysical parameters is known as reflection seismology. And the travel time curve for reflected arrival was the hyperbola, and in case of single layer model, the travel time curve with respect to offset distance square is equal to x square by v naught square plus t naught square, where x is the offset between the source and the receiver, v naught is the top layer velocity, and t naught is the zero offset time, that is two-way vertical travel time. Travel time curve for n layer geometry can be seen as tx square n plus 1, that means the travel time from the top of n plus 1th layer is equal to the x square by b bar n square plus tn square. Relation between ray path and travel time curve can be written as p is equal to sin I by b is equal to dt by dx. That basically gives you the ray parameter, which means the ray parameter can be found by taking the slope of the travel time curve. The root mean square velocity can be written for the Vn bar, and that Vn bar square is equal to summation over j is equal to 0 to n Vj square, that is the velocity of individual layer, or you can say the velocity of individual jth layer, multiplied to delta Tj, that is the travel time in the jth layer, divided by summation over j is equal to 0 to n delta Tj. And this is the Dix equation that we learnt, which is used to find out the interval velocity of individual layer. If you know the RMS velocity of nth layer and n minus 1th layer, so the interval velocity square can be equal to Vn square Tn minus Vn bar squared n minus 1 Tn minus 1 divided by Tn minus 1. So far, we have seen the Earth as a stack of velocity layers where individual velocities of the individual layers are uniform in nature, but in reality Earth is spherical and it has continuous distribution of velocity with depth, that is Vz, which signifies that velocity as a function of depth, and we are not considering the Earth as a stack of discrete layers. Rather, we are considering the Earth is continuous and the velocities are continuously varying with respect to depth. By Snell's law, we can write that P is equal to sin I by Vz, where velocity with respect to depth is given by Vz. Sin I, where I is the incident angle, P is the ray parameter. We learnt that as per the Snell's law, the ray parameter is constant along the entire path of the ray. The figure that is depicted here is taken from Stein and Weissation book, and it basically shows that the ray is emerging from the source position over here and being recorded at the receiver over here. When the ray emerges out from the source and it travels through the different layers, then at one point it bottoms up and then recorded at the receiver. You know that the velocities are keep on increasing as you go deeper down the earth, and the ray is experiencing increasing the velocity as it goes down, so it will move away from the normal, and at a particular depth it will be bottoming up and then being recorded at the receiver. So the path of the ray will be something like this, and the depth at which it will be bottoming up will be given by Zp, and the velocity is Vp if we consider it at this point. Then the ray parameter at this point will be P is equal to 1 by Vp, because the incident angle is 90 degree at this particular point. So what is written over here? If velocity increases with depth, sin I and I increases, because if you go deeper down the earth, the velocities are increasing, and you know that the Snell's law says that sin I1 by V1 is equal to sin I2 by V2, and you know that the V2 is greater than V1, since we are considering that the second layer velocity is greater than the first layer velocity or the top layer velocity. So we want to keep this particular ratio constant, then what we need to do? We need to increase the value of sin I as well. That means if the velocity increases with depth, sin I and thus I will increase. So the ray bends away from the vertical on its way down. Once I is equal to 90 degree, that means the depth at which the ray is bottoming up, the ray turns, becomes horizontal and then goes upward. At the deepest point, the ray parameter will be equal to 1 by Vp, or you can say 1 by Vzp. The expression for the distance traveled by the ray can be written xp is equal to 2 integral 0 to zp tan I dz, which means that we are just considering the ray when it is going deepest point, that is the zp depth, and then coming up. So first we are calculating the distance it travels as it reaches to the deepest point, and then we are just doubling that up so that we can find out the total distance traveled by the ray. We know that the distance traveled by the ray x is equal to h tan I, that we learnt in the previous lecture. So the total distance, because the earth is continuous, so we can write 2 0 to zp integral tan I dz. Dz is the depth it basically traveled. So that will further be equal to 2p integral 0 to zp 1 by v square minus p square dz, because we know that sin I is equal to pv, because that the Snell's law says. We can find out the value of tan I over here using some trigonometric relations, and when we use those trigonometric relations, then tan I will basically be equal to 1 by v square minus p square. And when we incorporate that into this particular expression, then it will become something like this. So if on some portion of the ray path the velocity decreases with depth, the ray bends towards the vertical. The ray does not turn upward until it gets below the low velocity region. So if suppose the velocity of the layer down below is smaller than the velocity of the upper layer, then the ray will not move away from the normal, but it will move towards the normal, and it will do so until it will not experience the increase in the velocity. Now if we write that expression for the distance in terms of the slowness, then we can write this expression u is equal to 1 by vz, where v is the velocity, and we can replace 1 by vz by u, then it will become 2p integral 0 to zp dz divided by u square z minus p square to the power under root. Similarly, you can write the total travel time, and total travel time you can write like if we consider this small triangle over here, then we can write ds is equal to dz upon cos I. And if we want to find out the time that it takes to cover this ds distance, then we can divide this distance by v, velocity, over here at this particular point. Now that is what we are doing over here. Travel time will be 2 integral dz 0 to zp dz divided by vz cos I, that is equal to 2 integral 0 to zp dz vz 1 minus p square v square to the power under root, that you can do it using sin I, that is equal to pv, and you can use some trigonometric relations to find out this value. So that will further be equal to, in terms of the slowness, 2 integral 0 to zp u square dz by u square minus p square cos I. This integral is valid everywhere except at the exact bottom of the curve where uz equals to p. So when uz will become p, because what is happening, we are writing p is equal to sin I by v, and at the depth where the ray is bottoming up, the sin I will become 1 because I will be 90 degree. So at that particular depth, this p will become v 1 by v. When you incorporate p over here 1 by v, because u is also 1 by v, so it will, entire thing will become infinity. So we cannot apply this integral at the depth of bottoming up where the rays start to go upward. Now the formulation, the travel time curve formulation can be seen as an interesting insight for data analysis if we do this formulation in terms of intercept slowness. And if you look at this particular figure, then you can see the top layer, there is one layer, there is another layer, there is third layer over here, and the ray is basically emerging out from the source and then traveling into the second layer, and then top of the third layer it is basically having the reflection, and then it starts to come back and then travel to all the layers and then recorded at the receiver. So if we consider this particular ray path over here, let's rub it down. If we consider this ray path over here, then you can see that the total distance the ray is traveling, if we consider that as x1 and that as h1, then it will be v1 delta t1, and in case we are considering the ith layer, then this will become xi and this will become hi. If we want to write it in terms of Pythagoras theorem, then vj delta tj will become xj square plus hj square to the power under root. The sin ij can be written xj divided by xj square plus hj square to the power under root. That will be further equal to xj divided by vj delta tj, and cos ij can be written hj divided by xj square plus hj square to the power under root, and that will be hj by vj delta tj. Now we can write vj delta tj from this particular expression. This can be written as xj square plus hj square divided by xj square plus hj square to the power under root. So basically this is what it is written over here, and then if we just factor it, then what you will see, this can be written as xj multiplied xj divided by xj square plus hj square to the power under root plus hj into hj divided by xj square plus hj square to the power under root. So this particular term over here is sin ij, and this particular term over here is cos ij. So this is what was written over here, xj sin ij plus hj cos ij. We can write this particular thing, or you can say you can rewrite it after you take this vj down below over here, vj and vj, then this will become like this, and this particular thing over here is your horizontal slowness, and this thing is your vertical slowness neta. So this is your P and this is your neta. So this thing will become Pj xj plus neta j hj, and you know that the ray parameter remains constant along the entire path of the ray, or you can say the horizontal slowness is constant. Then what you can write is that this can become P xj plus neta j hj. Okay, so just concentrate on this term. What you are seeing is that total travel time, or you can say the travel time of the ray that it spends in a layer, is the sum of the horizontal slowness times the horizontal distance traveled and the vertical slowness times the vertical thickness it travels. So you can see it is the product of P into the horizontal distance the ray is traveling plus the vertical slowness times the vertical distance the ray is traveling in the layer. Now we know that the P is sin ij by Vj, that can be written as Uj sin ij. Neta is cos ij by Vj, that can be written as Uj cos ij. And we also know that the P square plus neta square is equal to U square, slowness square, and slowness is 1 by V. So it can be written as 1 by Vj square. Now if you write the total travel time, then total travel time, as you know, we can write it del Tx is equal to 2 into the one-way travel time. So it will take total travel time as the downgoing time plus the upgoing time, and that can be rewritten as we, if you will replace this delta Tj from this particular equation over here, then it will become something like this. So 2 summation over 0 to n Pj xj plus 2 summation over j is equal to 0 to n neta j hj. By Snell's law, the horizontal ray parameter is constant along the ray path, and we can write Pj as P because it is constant along the along the entire ray path, and Px is equal to Px plus 2 summation over j is equal to 0 to n neta j hj, and this term is nothing but your intercept time. So if you will look at this equation and compare it with y is equal to mx plus c, that is the line of the equation of the straight line. So m is your p, that is your ray parameter, and c is the intercept time, that is this particular value. So tx will be equal to px plus tau p. So this particular intercept time we have represented it by tau as a function of ray parameter, where tau p is 2 summation over j is equal to 0 to n neta j hj, that can further be written as 2 summation over j is equal to 0 to n 1 by vj square minus p square to the power under root hj. Since we can write this neta j as cos I by v, so cos I can be written using sin I is equal to pv. So if you will replace it with that term, then it will become something like this. And then further in terms of the slowness and the ray parameter, it can be written something like this. So this is your equation 3 and this is your equation 2. Now you can see this is the travel time curve. If you take the tangent at any point, then the line of slope will be intersecting the travel time axis at a particular intercept over here. So this intercept is the tangent line to the time axis. In general, tau and p differ for different points. Like if you will take the tangent over here, then it will be something over here. So this will be your intercept time. Likewise, if you take somewhere over here, then it will be further down below somewhere over here. So you can say that the intercept time is depending upon the value of t and x, or you can say it is depending upon the value of the intercept time and the ray parameter, that is tau and p. So thus the function tau p is called the intercept slowness representation of the travel time curve. Now if we take equation 2, that was Tx is equal to Px plus tau p, and then we take tau p is equal to t as a function of offset minus px, and then differentiate it with respect to p, that means d tau by dp. Then what you will get? You will get dt by dp minus p dx by dp minus xp, that is equal to dt by dx into dx by dp. This has been multiplied with dx on the numerator and the denominator as well, minus p dx by dp minus xp, and then these terms will be cancelled out. What you will be remain with? Minus xp. So you can see that the tau p curve, the slope of the tau p curve is the negative of the offset distance. The slope of the tau p curve is the negative of the offset distance. Now, if you consider a single layer model where the top layer velocity is v naught and the distance between source and the receiver is x, or if you are, or you can say x naught, then x naught will become x by 2, and then the ray parameter that you can write is, that is sin I by v. Then you can say that that can be written x by 2 by v naught in bracket x by 2 square plus h naught square to the power under root. Likewise, you can write the vertical slowness neta naught, that is for the 0th layer, that means that is neta naught, because p is constant, so we are not writing as p naught, it will remain p always. So neta naught is equal to h naught by v naught x by 2 square plus h naught square to the power under root. Tx is equal to px minus 2 neta naught h naught, and then when you will incorporate these things into this equation, then what you will get is this, and then finally the tx will be equal to x by 2 square plus h naught square by v naught to the power under root. So tau p formulation also can lead to the travel time distance curve if you consider the tx variations. So which is familiar with the hyperbolic curve, and to see how this travel time curve appears when written as tau p, we can write equation 3, that is your equation 3. We can write equation 3 as this thing, and then when you will rearrange it by keeping p somewhere over here and writing it in terms of tau and p, and the variables are tau and p, then what you will get? You will get this equation. And this is nothing but the equation of an ellipse whose axes are tau and p axis. And so this is your ellipse over here. You can see this is the ellipse over here, and this is in the form of tau as the y-axis and p on the x-axis. This is your p, and this is the travel time curve for the same reflection ellipse. So this is your hyperbola, and this is the slope distance curve, and for the same curves that are shown above. Now what you will observe is that when you see the ellipse, when it is intersecting the tau axis at p is equal to 0, then the value of the intercept will be equal to two-way travel time, that is 2h naught by v naught, and that basically is the 0 offset point, that is x is equal to 0. And when this ellipse intersects the p axis at tau is equal to 0 and p is equal to 1 by v naught, that is basically representing that the slope of the travel time curve is v naught, 1 by v naught, that is similar to the direct wave arrival. And what you can say that the direct wave is similar to the reflection if tau is equal to 0, where p is equal to 1 by v naught. We will see how it is. Hence the line for the direct wave mapped to a point in tau p plane that is on the ellipse describing the reflected wave. To understand why this occurs, we can take xp as minus of d tau by dp. That can further be written as something like this. If you say that p is equal to 1 by v naught when tau is equal to 0, then what you will observe, xt will become infinity. Which means that when the offset distance is infinity, then the reflected wave will become similar to the direct wave. So that is what, like, let's suppose this is your surface and here you have the source and here you have the receiver and this is the single layer. Then this is, let's suppose this is your direct wave that is traveling to the receiver and the distance between the source and the receiver is very large. Then in that case it will be looking like that the reflection is almost similar to the direct wave. And the head wave is easily mapped into tau p plane because it travels time curve is THX that we have derived in the previous class will be x by v1 plus tau 1. So if you look at the head wave here, so this is your head wave, this one, and this basically asymptotically touches the hyperbola and here it is touching, and when you will extend it further, then it will hit the time axis at particular this point, and this point will correspond to this particular point on the ellipse, and this will basically give you the value of the slope of the head wave, and this will be equal to 1 by v1, and that is the value of the ray parameter of the head wave over here. So this is what it is written: a line with a slope equal to the reciprocal of the half space velocity p is equal to 1 by v1 and intercept tau 1. Thus, the head wave maps into a point on the ellipse describing the reflected wave corresponding to the critical distance xc. So the distance will be, so this distance at which it is touching over here asymptotically, then when you will extend it further onto the distance axis, this will be your xc, and if you go onto the slope axis, the head wave is touching over here asymptotically, and then if you will extend it further to the slope distance axis, then it will hit over here, and you can see that this is your 1 by v1 slope, and here it is your critical distance xc. For the case of multiple layers, the tau p curves corresponding to reflection of successive layers are all portions of different ellipses. So you can see that there is this head wave for the top layer, and then there will be reflection from the top of the second layer, that is hyperbola. From the top of third layer, this is the another reflection hyperbola. From the top of the fourth layer, this is another reflection hyperbola, and there will be head wave from that will be traveling at the interface of the top layer and the second layer. There will be another head wave, there will be third head wave that will be traveling across the interface of third and the fourth layer, and the corresponding ellipses will be for the reflection hyperbolas will be something like this, you can see over here. And then for a continuous velocity distribution, the summation for tau becomes an integral, that is tau p is equal to 2 0 to zp neta z dz is equal to 2 0 to zp 1 by v square minus p square to the power under root dz. That can further be equated to 2 integral 0 to zp u square minus p square under root dz. So formulating travel time curves as tau p is useful for some techniques that invert for velocity structure. So the summary: for a continuous increasing velocity model, at deepest point, the turning or the bottoming depth zp, the velocity is the reciprocal of the ray parameter. Distance traveled by the ray will be given as the integral 0 to zp tan I dz, that will be doubled, is equal to 2p integral 0 to zp 1 by v square minus p square dz. Time taken to cover distance xp by the ray is equal to delta tj is equal to xj sin ij by vj plus hj sin ij by vj, and this thing is your horizontal ray parameter pj xj plus neta j hi hj. The function tau p is called the intercept slowness representation of the travel time curve. P is the slope of the travel time curve. Tx, the distance x, is the minus the slope of the tau p curve. The head wave maps into a point and hyperbola maps as ellipse on the tau p plane. These are the references, and we will meet in lecture 5 of module 5 in the next lecture. Thank you so much. Bye bye.